Okay. Good afternoon, everybody. It is my immense pleasure to introduce our speaker of this week in our Water Resources and Environment webinar series at Universidad de Chile. So today we have Dr. Lieke Melsen. Lieke works as an assistant professor in the field of computational hydrology at Wageningen University, the Netherlands. Her research focuses on the selection and use of models, considering modeling as a socio-technical activity and the consequences of model uncertainty. To this end, Lieke combines technical approaches such as model ensembles and sensitivity analysis with quantitative research methods like interviews and ethnographic research. So today, Lieke will talk about her work in hydrological modeling. So Lieke, thanks a lot for accepting our invitation. We are very happy having you here, and the stage is all yours.
Thank you so much, Pablo. Thank you for the introduction. Yes, so what I will talk about today, if I'm correct, you should see my screen by now. What I will talk about today is that it will take a village to run a model. All right. So let's first clarify what we mean with model. And in this particular case, I'm talking about numerical models which describe hydrological processes. So basically the one you see on the drawing right here. So if I have to give you a definition of model, the one that I like most is a hypothesis of how a system works, codified in quantitative terms. So these are the kind of models I talk about today. It's not about scale models. It's also not about data-driven models. It's about these numerical models which contain hypotheses of how a system works. And these models are popular these days, especially in hydrology. Well, actually in all earth sciences, but hydrology is very much model-driven. And I can actually prove that to you, because in this study, they investigated for all papers that talk about runoff, which is one of the key processes in hydrology, as you all know, that already in 2010, so that's already 12 years ago, I mean, time flies, 70% of the peer-reviewed published papers on runoff already contained model, or already involved a model. So what we can see is that the majority of the scientific literature in hydrology includes models, which means that we might put some extra attention to where these models are coming from and how these models were constructed, because we actually learn from them, or we're supposed to learn from them. So the very first question, or when we start working with a model, we go through a few steps. So usually what we say, these are the classic steps that they prescribe when you work with a model, is that first you decide on the processes that are relevant, right? So you're walking through a catchment, if you're going there at least, trying to understand, are snow processes relevant? Is it the vegetation that I need to understand? So you create a perceptual or conceptual model, which is basically a drawing of the relevant processes. Then the next step is to decide on the equations. So now that you know that snow is relevant, will you go for a degree day method, or will you go for a radiation-based method? There's all kinds of equations that you can choose from based on your data availability, based on your understanding, based on your modeling philosophy. Then the next step is to get these equations into your computer. And if you're talking about differential equations, it often includes choosing a numerical scheme, for instance. So you have to somehow put all these equations together into your computer code. Well, then you can finally start running your model. You can start to create output, and then you can do your calibration, your sensitivity analysis, all kinds of things that you do in preparation of running the model for real. Because then finally you will evaluate it, hope that it performs well, or go back to the start and start all over again. Well, this is the very classical way of how literature describes how we work or build a model. But of course, in practice, it's not how we do it. In practice, if you read papers, hardly any paper goes from the first step all the way to the last step when they apply models. Usually, the first few steps are simply replaced by selecting an existing model, by selecting a model that's already available. So we don't think about the processes ourselves, so we select a model that we think fits the relevant processes in our catchment. And now that we saw that models are so relevant in hydrology, now that we saw that the majority of papers published in peer-reviewed journals use models, you can understand that selecting this model is a very critical part of your model study. So how do we actually select a model? This was a question that a colleague and I, Nans and I, asked ourselves, like, how do we select models as hydrologists? Because we have this feeling that in principle, we have the theory that the processes should be reflected in the model, and based on that, we should select a model that's fit for purpose. But is that really what we do when we select our model? Well, in order to investigate that, we did a bibliometric analysis. So what we did is, in this case, we drew 1,529 papers from Scopus that all use one of these 7 models that are mentioned there. So HBV, top model, GA4J, MHM, PRIMS, SAC, and FIC, which are all popular hydrological models. So in any of these 1,529 papers published between 1990 and 2080, one of these 7 models, at least one of these 7 models was used. And then we extracted data from all these papers. So here you see an example of a paper in our database. And what we extracted, we did some text mining, is first of all, the affiliation of the first author. We looked in the abstract if there's a country of application, so in which region was this model applied. We looked for certain landscape characteristics that were mentioned in either the keywords or the abstracts. And then, of course, we linked it to the model that was used. And this was sometimes, we had to do a manual check because you see that in this particular case, the FIC model was used, but it was also conducted in Victoria, Australia, or one of the authors was from there. So we also had to manually check that we actually really refer to the model and not to any other issues. So we extracted all these kinds of information. Also, we looked for the variable of interest, for the spatial scale that the model uses, for the temporal scale that the model explores. And for all these characteristics, we extracted them for these 1,529 papers. Of course, not every paper contains every piece of information, but overall, we got a quite good picture. And then we start asking ourselves, can we link which model was used to particular characteristics? Because that would explain to us why we selected that model. Well, first of all, what we saw was a very clear geographical bias in model use across the world. So what you see here is a global map, and the color of the country indicates how often this model was used in this region. And then the arrow indicates where the author is from, and it's pointing towards the region where it's applied. And what you see that FIC is, for instance, very popular in the US and China, while HBV is much more popular in Europe, and SAC, again, is more popular in the US. And actually, the pattern that we recognize here is that we see that models are usually applied close to the region where they were developed. So HBV was developed in Sweden, and we see that it has a very strong application in Sweden, even though there are applications in the middle of Africa as well. SAC was developed in the US, FIC was developed in the US with PhD candidates originating from China, which can explain that link. So we see a clear geographical bias in model use across the world. Of course, that can still mean that a model is selected because it contains the right processes, because there might be a geography in relevant processes. But in order to check that, we did our keyword analysis. So the first thing we looked at was the variable of interest. So let me explain the graph that you're seeing here, the mosaic graph. So we had 478 papers that contained a variable of interest in the abstract or the keywords. For instance, in this case, water resources. So from these 478 papers, many of them mentioned water resources. And you see on the top row, you see the 7 models. And then the width of the block indicates how many papers that use that model have water resources as a goal in their abstract. So what you basically see here is that all 7 models have papers affiliated to them, associated to them, in which water resources is a variable of interest. And you see that in this particular case, PRIMS is relatively more frequently used for water resources studies. But most important, all 7 are used. We did the same for floods. You see that for floods, 5 out of 7 models are used. So in this particular case, MHM and PRIMS didn't have any flood application, not at least in our database. We see that the majority of models, 6 out of 7, are used for drought studies. We see again that the majority, 6 out of 7, are used for water balance studies. We see again that 6 out of 7 are used for low flow studies. So basically what we see is that all models are used for almost everything. So whether we are studying floods or droughts or water balances, extremes, high flows, low flows, these 7 models can be used for it, or at least they are used for it in these papers. So apparently the variable of interest, so whether we're interested in a flood or in a drought or in a water balance, doesn't determine which model we select. We could apparently use either one of them. The same is true for the temporal scale. So what you see here is that all 7 models are used for prediction. Well, prediction is pretty generic, but 6 out of 7 are used in a climate change context, while also 6 out of 7 are used in a forecast context, which is of course a different time scale. They're also used for projections and for seasonal forecasting. So basically, again, here we can say that all models are used for everything. So apparently also the temporal scale cannot really explain which model we select. Apparently, whether we look at the long-term future or the short-term future doesn't determine which model we choose. Well, it's becoming a bit repetitive, but the same is true for the landscape. You see that the models are used in arid regions as much as they are used in alpine regions, in mountainous regions as much as they are used in urban regions. So basically, these models are really used across a whole variety of environments, which means that we don't necessarily select them because they have particular processes that are relevant in particular environments. These models are used as models of everywhere and everything. Same story for the spatial scale, regional, global, catchment scale, continental. These models are used there. So basically what we conclude from this is that model selection is not based on which processes are relevant or which variable of interest we're interested in or which temporal spatial scale we're interested in. Apparently this doesn't drive model selection, but then what does? Well, what we did find is that in 74% of the cases, and this is a lower estimate, in this case we were really strict on ourselves. In 74% of our cases, so of these 1,529 journals, we could correctly predict which model was used based on the affiliation of the first author. So it has nothing to do with which process is relevant or which time scale or which temporal scale or which kind of environment. It was the institute of the first author that best explained which model was used. And from that, we drew the conclusion that model selection is, generally speaking, based on legacy rather than adequacy. So it's explained by convenience, experience, habit, practicality. We use this model because we know how it works. We use this model because we have experience with it. We use this model because we have the infrastructure to prepare the input data. We use this model because it's efficient. So all these kind of legacy arguments drive model selection rather than this adequacy arguments, like it has the right processes or it has the right temporal and spatial scale. Probably also, I mean, I don't say that modelers are making wrong choices. It's just not driving their final selection. Final selection is based on legacy. And this is something to consider, given that a different model will lead to different results, right? And this is something we will see later. So model selection is driven by legacy. It's driven by experience at a certain location. And this is a self-sustaining system because I analyzed vacancies in hydrology. And what you see, just as an example, I drew these vacancies from the About Hydrology mailing list. So I guess many of you are a member of this mailing list, and it gives a lot of announcements of PhD positions, postdoc positions in hydrology. What you see, for instance, in the upper bar is for the PhD positions. There were 204 positions that I found in this mailing list, and 152 of those contain any modeling. So 40% of these vacancies was purely modeling, and 34% was partly modeling. So this already reflects how much attention we pay to modeling in hydrology, right? Because, I mean, 74% of the vacancies involves any modeling. But what I saw in these vacancies is that they often already prescribe which model has to be used. So here you see an example that I encountered in these vacancies where it says, the PhD candidate will set up an ensemble of runs with this model, TSMP PDEF. I don't know this model, but apparently that's a model for the African continent. So there's nothing to choose for the PhD candidate here. This PhD candidate applies to a job and is forced to use this model. Sometimes it wasn't necessarily literally mentioned which model was used, but some particular experience was prescribed. So experience, for instance, with SWOT. And of course, you can imagine that that probably indicates that SWOT will be used in the project. I mean, it wasn't written as such in the vacancy, but they liked people with experience with these models. And actually what I saw is that in 30% of the postdoc positions that include any modeling, specific models are already used in the vacancy. So this means, as a postdoctoral researcher, you already finished your PhD, you're an independent researcher, you're looking for a new job, and then already you got prescribed which model you should use. And that's because this model is so much attached to the institute. So you apply at a certain institute and you're forced to work with the model at these institutes. And this is how we create a self-sustaining system, right? Because this is how you, as a postdoctoral researcher, contain experience with this model. You work at this institute. It becomes easier to work with this model because you gain experience from your colleagues. And this is how we sustain the system of institutes working with particular models. And this is how we build our toolbox of models. So model selection is driven by legacy, and we know that different models will lead to different results. And we know that we actively sustain the system in the way that we organize our recruitment process. So here I'm giving an example from Professor Mendoza, who demonstrates that different models indeed lead to different results. So what you see in this particular example on the x-axis is three different catchments to test. So Yampa, East, and Animas. And on the y-axis, you see the runoff ratio. And then you see the runoff ratio given different model structures. So you can recognize some names because PRIMS and FIC were also in the previous analysis, but here also NOAA MP and NOAA LSM are included. And you see that the runoff ratio, the simulated runoff ratio, can vary quite a bit if you choose a different model structure. So what we saw previously, model selection is very much inspired or prescribed by the institute, by the location where you are. But we also see that model results depend on which model you select. So basically, the institute determines the model results, which is not necessarily in line with what we want it to be, right? It's not some kind of objective truth then. But there's more, because this is just model selection. But what Dr. Mendoza also showed is that decisions beyond model structure influence model results. So what you see, for instance, in panel B, when we select the PRIMS model and we continue with this model, so we're at an institute where PRIMS apparently is the standard. And then what we can choose, we can choose which objective function we use when we calibrate our model. So do we use the Klein-Gupta efficiency or the root mean square error, which is related to the Nash-Sutcliffe? And you see that also those decisions lead to different runoff ratios that we simulate. We can use the different local optima that we obtain from calibration. We see that it leads to different results. We can make different choices in which forcing data we use, and we can see that it leads to different results. So, there's already the first step, which is model selection. But once we selected the model, once we're at this institute that tells us which model to use, we still have to make a lot of choices as modeler. And also these choices influence the model results. And that's why we don't only need to investigate the model itself, but we should also start to investigate the modeler, because how does the modeler make these choices? And how does the modeler justify these choices? Because each of these choices leads to different results. Oh, what's this? Do you still see my screen? It got black here, but it's fixed. Good. So what I did, I conducted 14 in-depth interviews with modelers from 3 different institutes. And these interviews were conducted between February and June in 2020. I interviewed 3 group leaders, 4 senior researchers, 4 postdocs, and 3 PhD candidates. So basically, I cover quite a broad range of experiences with modeling. And I collected about 14 hours of material, so 14 hours of talking models. And what I did is I analyzed basically what I did is for each of these interviews, I read the most recent paper of this person in which they used a model. And I asked them really annoying questions like, why did you choose this model? Why did you choose this calibration algorithm? Why did you choose this objective function? Well, like this. It was a nice conversation, but annoying questions. And in the end, I could identify 87 different motivations why people make particular choices. And here you see an overview of the choices that I identified. And you see that the size of the dot is proportional to how often this motivation was mentioned in the interviews. So experience from colleagues, which I will clarify later, is the biggest dot because that was the most frequently mentioned motivation by the modelers to make a choice in a particular way. I was able to classify these 87 motivations into 7 different classes that you can see on the left-hand side. And I will go through an example one by one for each of these classes. So for instance, one of the motivations to do something in a particular way was because the funding agency told the modelers to do so. So in this particular case, for instance, the funding agency said, you need to use this forcing data set. Most cases because the funding agency created this forcing data set, so they wanted to know how it performed. So there was no choice for the modeler which forcing data set he or she wanted to use, because the funding agency already prescribed this choice. So this is what I classified as an external party that's providing a motivation to do something in a particular way. Another motivation that I encountered quite a bit is literature. So they said, I did something because I found it in literature. So, that's a very valid reason for scientific progress, right? We publish and then we learn, and then the next person builds on that. And this is something that's organized by the scientific community. So this literature motivation I assigned to scientific community. Sometimes there was, for instance, a modeling into comparison, or a modeling into comparison had happened in the past and the same model setup was used. And then the motivation came from a modeling protocol, because they said, well, we had this intercomparison and we had to obey the protocol that was assigned to us by our partners. So this is introduced by a scientific collaborator. Then, of course, computer power was sometimes mentioned as a reason. So why a particular resolution? Well, very often because computer power is actually creating certain opportunities or not. And actually, computer power is very much tied to the institute, because some institutes have access to high performance clusters, others don't. Or others have access to a local cluster and others have access to a supercomputer. So computer power is, well, generally speaking, determined by the institute. Then the most frequently mentioned motivation to do something in a particular way is because a colleague has experience with it. And this is, of course, assigned to the team of the modeler. So the modeler is working in a particular team and relies a lot on experience in the surrounding of this modeler, so in the near vicinity of this modeler, the team. And you see that that's really most frequently mentioned. Then as an individual, so as a modeler yourself, as a person who's doing the modeling, you can also make choices, and sometimes you have no real reason. So sometimes I ask, why did you do it this way? And it's like, yeah, no real reason to do it. I just did it that way. And some choices can be called consequential. They are the consequence of choices you made earlier. And this can be strict or this can be less strict. So in this example that I circled now, the default model tool, what you see is if someone selects a model, this person also often selects the default calibration algorithm that comes with the model. Of course, you're not strictly forced to use this calibration algorithm, but you might as well, because it's easy. So because you made a choice for a certain model first, then the consequence is that you probably use a certain calibration algorithm. So these are just examples of all the kinds of motivations that I encountered when I asked for reasons to do something in a particular way. The one that I didn't discuss now yet is this fission that you see in the left in gray. And that's because I couldn't classify this one so clearly in these 7 classifications. But the vision relates to the kind of modeling philosophy or school of thought of the modeler. And I think this is a very important one. So it means some people really like a reductionist approach. They really believe in super high resolution, describing all the processes in as much detail as you can, couple as much processes as you can. And others believe more in conceptual models, simple buckets, as few parameters as possible. And really, this comes down to the level of religion, because there is no way of ever determining which one is better. There's no right or wrong. There's no better or worse. It's just different approaches to the same question, namely, how does this hydrological cycle work? So that's a vision, and it's a vision you develop over time, and it's a vision that you develop based on experience and based on your colleagues and based on your background. So a vision is a little bit of everything. But now that we had these 87 motivations that we could classify into these 7 different classes, and then we had this vision on top of it, we can classify them again, because some of these motivations really had an epistemic character. That means these choices in modeling were really made to promote the truth-like character of science. So I'm really saying these motivations are well-founded. You really made this decision because you sincerely believe that this is going to bring you to the real correct answer as good as possible. And then you can think, for instance, of, I tested it and this came out as best. Or I tried different methods and this method led to the best performance. Or these are simply the best available data. So those are epistemic reasons. You did something because it really leads to the best result according to your standards of best. And of course, your vision is also something you believe in your vision, and that's really, you're convinced that that will lead to the best results. So these are the motivations that are epistemic. Then literature is a bit in the middle, I would say, because in literature, of course, you can do cherry picking. You can have a certain opinion and then you can look for the papers that fit your opinion. I mean, I guess we all did it, that we wrote a certain sentence and then we say, look for a reference that says this, right? Yes. So yes, we can look for confirmation in the literature, but we can also be open and just look for what the literature teaches us. So literature is a bit in the middle. But now look what's in the contextual group. You see? The majority of the choices we make in modeling are based on context. They depend on which colleagues you have. They depend on which computer power you have access to. They depend on data availability. They depend on your personal judgment. These are all decisions that you will make differently if you're at a different place at a different time. And what we just saw from the results of Dr. Mendoza is, if you make these decisions different, you will get different results. So, I mean, now it's getting serious because, first of all, we choose a model because we're at a certain institute, which basically means if we go to a different institute, we will select a different model, which will mean different results. But then once we selected this model, we will also make all these decisions based on where we are and based on our experience and based on the colleagues that we have, which will lead to different results. So what can we actually learn from models if all the choices related to models are so context dependent, even though we know that these choices lead to different model results? And that's a sincere question I have. That's a sincere worry I have. It contributes to the methodological uncertainty, because if we're talking about hydrology, we often talk about technical uncertainty. We sample the parameters, or we sample the model structures, or we sample what else do we sample? Sometimes the input data. But all these tiny decisions that we make as modelers also influence results, and we don't ever sample those. While they all contribute to uncertainty, different decision, different result. Different time, different choice, different result. Different place, different choice, different result. And also here we see the self-sustaining system. We have a team. As an individual, you start working at a certain team. So you apply for this job, which tells you that you can work with this fancy model, or that doesn't tell you to work with a fancy model, but you find out once you start there. And then you start internalizing the procedures that are standard in this team. So you depend a lot on the experience from your colleagues. Then you learn how they do it. Then you start internalizing, like, okay, this colleague is always using this calibration algorithm. Well, after a few years, you are the one telling your younger colleague, you should use this calibration algorithm because it works well. And this is how you sustain inside the team this certain experience, and you internalize certain processes. Of course, it also works the other way around, right? If a new person comes to a team, this person can introduce new methods, and these new methods can become institutionalized. So you have a new calibration expert entering the team, and this calibration expert says, well, I would use Markov chain Monte Carlo. Why are you using this all the time? And then, well, you can start institutionalizing such a method. And then you can internalize all the other methods again. So we're creating a system where modeling teams basically create their own ecosystem. And of course, this is actually a local application of the famous paradigms and the paradigm shifts if someone enters with new ideas. So we know model selection driven by legacy, but we also know different models lead to different results. Methods, choices in modeling driven by experience from colleagues in often cases. And we also know different choices in methods will lead to different results. And as I said, for me, this is a sincere problem, because what does it mean? What can we actually learn from models if this is the case? And I think there's some things that we can improve as community to at least have a better grip on modeling. Because as I said at the beginning, the majority of the papers in hydrology depend on models. And now we saw that the model results are so much context dependent. So the first thing I think we should do is really to move motivations from this contextual to this epistemic side. So we really want to make the share of motivations that are given by context smaller. So as a modeler, you should better think about the decisions you make. You should think of better motivations or better underlying reasons to do something in a particular way. There's still no right or wrong. There can still be disagreement, but at least it's something that needs to be thought about. And I think some good modeling practice guidelines can stimulate you with that, like really make you carefully think why you made particular choices. Of course, there will always be contextual choices left. There will always be time constraints to your project. There will always be limitations to your computer resources. And there will always be data availability issues or not that determine practicalities in your project and that will influence your model results. That's always the case. It's unavoidable. So to some extent, we will have to accept it. Second is that we actually should think better about the decisions that we make. So we should determine which ones are most sensitive and then really look for those for good reasons to make those choices. So maybe indeed calibration is a very sensitive decision, which calibration algorithm or which objective function. Then we should carefully decide why we use a particular calibration algorithm or why we use a particular objective function. As I said, you can still have disagreement, but at least there needs to be epistemic underpinning. There needs to be a good reason rather than a no real reason, because we know that this influences the results really well. Furthermore, I would really encourage modelers to be explicit about their modeling vision. So do you really believe in a reductionist approach? Do you believe in being detailed about every single process that happens in your catchment? Or are you more from the conceptual level, which is also fine, but then your epistemic choices relate to your vision. So you make choices in a particular way because you believe that that's the best way to model. And then you can justify these decisions based on that. And then you can have an open conversation about who, well, not about who's right or wrong, but at least you can know that there's different perspectives. And that's basically, I guess, my key point, that each model study is showing a partial truth. So a different model or a different institute, a modeler at a different institute will come up with different results because of everything that we discussed so far. And we will see that as a partial truth. That is the truth encountered with that model in that context at that institute with those choices. Then someone else comes from another institute with another choice and other decisions, and that's another partial truth. And we can find out what's actually happening if we combine all these partial truths. If we have 20 institutes with different visions and different models, and they all point in the same direction, then we can start believe that maybe something is going on there. But if they point in opposite directions, it basically means that we're inside our uncertainty band. In terms of time, I think I might step over this one, but just to make clear that so far we only discussed models in the context of, we're talking about a modeler, a modeling team at an institute. But of course, there's a much broader context. There's the context of, well, for instance, the commissioner, the funding agency, that's already scoping the question. Then as a modeler, you run your models and then you set the agenda. And this is very clear for climate change, for instance. The climate models have a particular result, and these kind of results steer policy decisions. They steer which points are on the agenda. They steer which paths are explored. And of course, certain results, if the model doesn't produce certain results, it will not be discussed in the policy agenda anymore. And finally, we will have a certain societal impact. So what I mean to say here, and this is a bit less strong for the scientific modelers, but more so for the practitioners, is that as a modeler, you're just part of a big chain where a lot of power relations and values and biases play a role. So what we discussed today now is really in the near vicinity of the modeler. But if you look at the broader context, the model plays a much bigger role because it can determine the agenda of policy decisions, which makes it even more urgent to think carefully about our decisions. So are models neutral? No. I know that many natural scientists tend to believe that models are objective truths because they describe the laws of nature and the laws of nature are just there. It's not the case. We don't know the laws of nature. Maybe they don't even exist. We all have different understandings and we all have different experience in how we integrate them. So technology is not neutral. Models are not neutral. Actually, models are social constructs. They are constructed based on your experience, based on where you work, based on the limitations or opportunities that the institute imposes on you. And with that, I would like to end this presentation. I hope it's sort of positive still. And I'm very much open to questions. Thank you.
Okay, Lieke, thank you very much. That was super interesting. And welcome back, everybody. My name is Pablo Mendoza. I'm with Nicolas Vázquez from Universidad de Chile. We are broadcasting from the Department of Civil Engineering in our Water Resources and Environment webinar series. Today's speaker was Lieke Melsen, who has just finished a very exciting talk about modeling and also religion. And actually, Nico and I were discussing in between, and well, the first thought that came to my mind was that a lot of scientific findings are largely based on beliefs, which is crazy, right? I don't know if you could, I don't know, can you expand a little bit more around that idea based on your work?
Yes, actually, I find that, I mean, it's a nice way of summarizing it. And I think we can learn from the social sciences there, because I know that we natural scientists tend to think that we do cool stuff. But in the social sciences, it's really normal to reflect on your positionality. So whenever you're encountering a social sciences study, you will find a chapter positionality where the author or the researcher is reflecting on their own position. So what do I think? What do I believe? How does that influence how I look at problems or how I frame questions? And it would actually be very healthy if natural scientists, and modelers in particular in this case, would do that too. So if they would reflect on their own positioning, and then you can say, okay, we disagree about how we create knowledge. We disagree about whether conceptual or reductionist is better, or process-based, or whatever, physics-based. But it's okay to disagree. I mean, that's what science is about. And to be honest, there's not an objective referee out there who can ever tell you who's best. I mean, of course, the reductionist school can come up with proof that their model is best, but that's also based on their demands, or what they decided that determines what's best. So I think some introspection there, and actually a positionality chapter in each modeling study would be a very healthy development.
Okay. So that takes me to a second thought that takes me back to, to my PhD work. I always remember that Martin used to tell us, when you read a paper, be liberal. And I think I finally understand what
did he
meant.
say? What did he say?
Every time you read a paper, be liberal. Liberal.
Yeah. Yeah.
I think that I now understand, because many times when we start looking for papers in order to address a specific research question, of course we're biased, like towards people who thinks like us, and disregarding those. Well, it's kind of, I don't want to put it this way, but we I don't know, we're less likely to look for papers for specific people just because of the way they think. And I guess that you're totally right. Like, we should be more open-minded about it and
But it's not easy.
Ideas, and it's fine to disagree.
But it's also, I mean, I don't want to be judgmental about the current system. As I said, also with the vacancy, so we hire people to use certain models, or we hire people with certain experience. Of course, you can say, oh, it would be good to hire someone with a complete opposite vision, because that person can keep you sharp, etc. Yes, but it's also nice to collaborate with nice colleagues, or it's also nice to have a good team atmosphere. And I mean, there's good arguments. There's good arguments to do it the way we do it now. I think the system right now is very efficient. You can write a lot of papers as institute, because it's very easy to set up a model. I mean, there's not only downsides to how it's going right now.
Yeah.
It might be good to be a bit more critical on ourselves sometimes. Yeah.
Yeah, I fully agree with that. And I also was, I don't know, I was just thinking that it happens a lot in our team, that we have worked for such a long time together that we start to think the same way. I mean, and it's kind of crazy. Like, sometimes we are, I don't know, looking at each other's presentations, let's say for a conference, and this other guy puts a slide that I would put, and he writes the text that I would write.
Yeah.
And that, I don't know, that reveals this sociological aspect.
This internalization of processes. At the same time, I mean, you probably really enjoy working in this team, right?
Yes, exactly. And
it's also a very enjoyable experience. So yeah.
And when somebody in the team shows up with a question that puts up out of place, it's, I don't know, things get crazy somehow. Like, oh, why is he saying that, or why is she saying that?
Okay, I think I have a few comments in the chat. Some people says thank you for your talk. Sometimes the availability makes it like if we should use a specific model because it is here. That's a comment from Maria Julia Wiener. And this is a comment and a question from Luis de la Fuente. He says, I completely agree about your findings. In fact, it is even worse because our models controls what we can learn and discover about the system.
Yeah.
So, and here's the question. So how would be your suggestion to deal with this issue?
Yeah,
well, that's a very hard question.
Yeah, but it's the key issue, because that's exactly what I was trying to say. We think we learn from these models, but basically we put what we understand in these models, right? So what can we learn from that? And that's really an epistemic or an epistemological question. And now I'm sorry to go into this much detail, but this really depends on your worldview. So if you believe, I mean, I go back to so you have ontology, which describes how you understand the world. And then you have an epistemology, which tells you how you can learn about the world. And apparently in hydrology, we have this epistemology that we think that we can learn from models. And if we go back to this vision again, some people think we can learn from conceptual models, and other people think we can learn from physics-based models. And they probably partially maybe even deny each other's results, like Pablo was saying, right? There's certain papers you don't pay attention to because you just disagree with this person or how this. So yeah, so basically you deny the knowledge they gained, which they consider valid in their epistemology and ontology. And that's why I say it would be so much easier if we would all just think about it, reflect on our own positionality. What do we believe and how do we believe we can learn from that? At the same time, I also have a positionality. I call myself a constructivist. So I really think that knowledge is socially constructed. So I don't believe in natural laws that are there universally true necessarily. And I don't believe that we can disentangle them with the models that we have. I only think that models can be an inspiration to look at things in a different way or say, okay, this might be an issue. Maybe we can look at it from that direction. So far for I'm quite reluctant in learning from models. Yes. But everyone will have their own vision on that.
Cool. Thanks, Lieke. Do you have any other questions?
No, I don't think so.
Okay, so I want to remind our audience that you can write your questions in the chat on YouTube. Lieke, you were talking about different aspects of legacy, convenience, experience, habit, practicality. How did you come to these concepts inside of the big box of legacy? Or is there an aspect that you did not consider or you have not considered in your work that should be part of legacy?
Yeah, so these aspects that I mentioned, they are not part of the results. They are part of the discussion, so to say. So based on our own experience, based on conversations with colleagues, we determined that often you have institutes have modeling ecosystems. So then it's just practical to work with this ecosystem, right? I mean, people say, if you work at a certain institute where they have a certain model and they're very experienced with this model, you just push a button and it gives results because they have the whole infrastructure set up to prepare the input data, to real time download the input data from a certain database, to put it into the right format, to run your model, and then to analyze the output. I mean, sometimes they have the whole infrastructure ready, which means that you're quite attached to this model because you have to push one button and you get model results. It's very tempting not to switch models then. Yeah. So these came from experience, from discussion, from literature, etc., but they weren't necessarily a direct result of the paper analysis, the bibliometric analysis.
Okay, thank you, Lieke. We have another question in the chat. Would it be appropriate to use supervised learning algorithms in hydrological modeling to train the model and thus reduce the variability in the expected results?
I don't know. To me, supervised learning, unsupervised learning, whatever you decide to do, again, you make a lot of choices.
Yeah.
So again, you introduce a bias based on your choices. So for me, any machine learning or other algorithm, any artificial intelligence is subject to the same kind of issues. You see, I mean, if you see groups working more on data-driven approaches, you see that in some groups they like long-term, short-term memory, neural networks. In other groups, they like random forest. I mean, you see the same kind of issues appearing, but then at a different level. So then we're not so much talking about how do you prescribe the process, but which technique do you explore? Or how long do you consider a sufficient training period? Or how supervised is your learning? Or how physics informed should it be? Yeah, so I see the same issues there.
Okay, thank you, Lieke.
And even harder to evaluate those. Because if we're talking about the classical numerical models with processes explicitly treated, at least you can say, like, I treat snow here and I don't treat snow. And you can have a discussion at that level. But I think if you're going in towards these data-driven techniques, it will be even harder to have a discussion on the content. It's going much easier towards the level of religion, I would say. But that's, maybe I should study it more to have a more
Yeah,
clear.
but no, I agree with you that regardless you're using a statistical or data-driven method versus a process-based method, you're always facing the problem, well, the issue of subjectivity. I don't think that it's necessarily a problem. It's just there.
It's just there, exactly. It's not something we can. It's not something we can solve. We have to accept and embrace it.
Yeah,
but acknowledge it. Yeah.
Okay.
So I think I have two more questions. This is a question from, I think it's Diego Hernandez, maybe, I don't know.
Yeah.
He asks, what do you think about the efforts of standardization in modeling? For example, common frameworks of methodological decisions making, etc. Are they contextual reasons?
Well, it's very interesting because we're currently doing a study about that in the Netherlands, where we have this good modeling practice handbook, and it's really an extensive handbook which describes how you should use a model and which steps you should go through. And of course, there's always a discussion on the level of detail. So this is very generic. It starts with you start with your sensitivity analysis, for instance, and then your calibration. It describes the processes at a very generic level. However, what we saw when we interviewed practitioners, so we interviewed modelers at the water authorities, they don't like this at all. Because modelers believe in their own experience. They think they can do good, and especially the name of this book, Good Modeling Practice. They say, so if I don't do it this way, it's bad. Like, it's very judgmental. So this book was developed by the whole water management community in the Netherlands, and still it's not used these days because modelers don't like it. And that's, I guess, the standard problem with standardization is that you cannot convince people to do it that way. It's too hard. And I mean, it's the everlasting discussion about the level of generality. So how detailed should it be? Or I mean, if you keep it too general, it's not providing any standards. And if you make it too detailed, models will not agree with it and they won't obey it. And I see this, and there's actually also a risk involved, and that's that even if people would accept these guidelines or these standardization rules, it basically would mean that everyone would start doing the same thing. But then it would also mean that we miss insights on the uncertainty because, as I said, I don't believe in the real method or the best method. There's multiple ways of doing something. And if we all start doing something in the same way, we lose track of uncertainty introduced by doing it in a different way. So besides that modelers are just too stubborn to ever accept such a standardization, I think it also decreases the insights in uncertainty, and there's a risk there. On the other hand, there's one thing that I really believe in, and that's good documentation. So there are guidelines for good documentation, and it would be great if modelers would do that.
Mm-hmm. Yeah, it would make life easier for everybody.
Sorry?
No, it would make life much easier for everybody.
Yeah, except that it's boring to do, right?
That's right.
Let's be honest, yeah.
So here's another question by Seb Diaz or Sebastian Diaz. How the deep uncertainty introduced by climate change changes the way how we interpret the outputs. Would you recommend a bottom-up approach to connect hydrological models and GCMs?
Well, actually, if we really talk about deep uncertainty, I mean, this person is referring to deep uncertainty, right? So deep uncertainty is really requiring a different approach in modeling. It really means fully exploratory, full force sensitivity analysis. I mean, if you can find a computer that can couple hydrological models with GCMs and then do full force sensitivity analysis, be my guest. But I mean, I think deep uncertainty is another level of uncertainty. I mean, those are the unknown unknowns. And there's some very interesting literature if you go towards the papers from Warren Walker, for instance. He was a professor in Delft and he really worked on deep uncertainty. I can really recommend his papers. There he really says, like, how should you model if you want to treat deep uncertainty? But it's really a next level approach. But then still, I think that all this can apply. I mean, if we're talking about deep uncertainty, then still you will make choices for a certain model. I mean, in the methods that he proposes, You still choose a certain model, you still explore certain scenarios and not others, etc. Yeah.
No more questions in the chat.
No, okay. Okay, Lieke, thanks again. It was a super nice talk and also very, very interesting conversation about models and science and religion. Why not? Okay, I want to thank everybody for staying connected. So we will meet again on October 13th for the next Water Resources and Environment webinar at Universidad de Chile. Our next speaker will be Mari Carmen Guerra. Okay, so see you in 2 weeks. Have everybody a good afternoon.
Bye.